a few topics, and then today we'll conclude on game theory. I think before we end, maybe we'll solve one or two questions on game theory so that you have an idea or a feel of um, how things are going to look like. But um, as far as today is concerned, we are going to iron out all the issues. We are going to answer all our questions because we want to close the docket on game theory. Okay, so I don't know if the groups are ready, the various groups. Let me cross-check on my list and see. So I think in total we have about 7 groups, if I recall. We have about 7 groups, and you can choose to present your work anyhow you please. Saying anyhow you please in the sense that maybe because you did the work together, you feel that one person should present it and then the rest of you will take questions or will follow through. Maybe some can decide that um, somebody will start, another will follow, and then the others, I mean, the question will come for the whole group. So, however you want to go about it, you can do that. So, I don't know if is Priscilla's group ready? So, Priscilla, if your group is ready, maybe you can. You are the only female. Okay, so one female in each group. That's nice. With the exception of the last group, we have Grace. Is Grace on the call? Hello, Grace.
Yes, madam.
Okay, are you the only lady in your class?
Yes.
Oh, I see. No wonder they treat you as a princess. Okay, so I think with the exception of the last group, each group has a female. So, Priscilla, your group, I don't know which group is ready. Priscilla, if your group is ready, maybe you can start.
Good afternoon, Doc.
Good afternoon.
Okay. So, Doctor, please, if you don't mind,
I
another group could
mind.
another group could start, and then we'll continue after that group.
Why so?
Um, we are ready though. We have our slides and everything, but then we just want to do some finishing touches.
Finishing touches.
We are done. Okay.
Yeah, so I
Yeah.
mean, so you can
Okay.
proceed. Oh, Grace, is your group ready? I know Grace will say no.
Madam, we are ready, but then we are ready.
Why
So,
the bat?
oh no, we are ready. How is it that we are ready? So,
Okay,
I
so
don't know. Somebody has to project it for us, right? So that's what I'm working on. So that you show the screen as we are
yeah,
reading through.
why are you not able to show your screen? You are not able to
I'm
share.
using yes. So let me try. That's what let me try. So you represent. We are ready.
Okay, so I asked Grace's group and Priscilla's group because I mean, According to the topics, it's best we deal with the extensive and then the sub games, then we move to the rest, right? So, which is why asked, I asked that either group 1 or group 6 should proceed. Grace, are you able to share? Okay, so as they are preparing to share the second group, which is Saviour's group, Savior, Josephine, Ebenezer. Josephine, the other time was Josephine in class?
Hello, madam.
Yes,
Hello.
sir. Yes,
Yes,
sir.
good afternoon.
Good
So I am
afternoon.
Inusa from Josephine's group 2, but
Okay.
I think she did not register for this course. I'm not sure she's part of this cohort.
Okay, because
Yeah.
I'm not sure I've met her, have I? So
No.
she's not joined the class yet, right?
Yes, for
Okay.
this semester.
Okay, that's
Yeah, so
fine.
we are actually 4 instead of
So
the
you are
5. You don't
4.
have to. Yeah,
Okay.
so
Okay. So as the first group prepare as the group prepares to share their slides and present, please kindly prepare yours as well so that as soon as they finish, you can proceed.
okay, madam. Thank you.
Oh, thank you. Grace,
Yes, madam.
what's happening?
Yeah, I'm trying to share my screen. Wait for me.
Guys, do you all see the share button? Or I'll need to, prompt the host to make you a co-host before you
I'm
can
sure
share.
she's using her phone to join.
No, please don't use your phone. Come on. So if Grace is not able to share, somebody else in the group should share.
So
The phone will not help us.
she has shared the slide with me. Let me project it.
So Evans is sharing my screen and my work so
So
that I
where
can
is
present.
Isaac, Enoch, Eric 1 and Eric 2?
We are here.
I think we did.
So why are you making the woman suffer
Madam, we
like
are
that?
here, but at the moment we don't have access to computers. I'm now moving to my computer.
Ayo, why is why is that the case?
I'm not home. I went out, so I connected on my phone.
Okay. So
So please, okay. So good afternoon, everyone.
good afternoon. How many
We
slides do
are
you
group
have?
7. 16.
Okay. So can we do this in the next, let's say
5
between
minutes.
10 and let's make it 10 minutes maximum.
Okay. Okay. So we are presenting on extensive form games, sub-game perfect equilibrium, which is the SPE. Okay, Evans, please. Next slide. So our presentation outline contains what is sub-game perfect equilibrium, aspect of sub-game perfect equilibrium, application of sub-game perfect equilibrium and advantages, the game theory, application of the game tree, and then sub-game perfection, application of backward induction, and then we compare the sub-game perfect equilibrium and then perfect Bayesian Bayesian equilibrium conceptually, then our references. So that is what we are presenting on today. So, Evans, please, next.
Enoch is the one sharing.
Hey, Enoch. Sorry.
Enoch, you can put it in presentation.
So can you see?
Yes, I can see.
Okay,
Please
all
hold it. Please make it bold a little. Okay, so what is sub-game perfect equilibrium? Sub-game perfect, or let me say SPE, is a solution concept in game theory used to analyze dynamic or sequential games. Okay, so sub-game SPE is a refinement of Nash equilibrium applicable to dynamic games where players' strategies are optimal, not only for the entire game, but also for every game that could be reached. This concept helps ensure that strategies are credible at every point in the game, thus avoiding non-credible threats and promises that could undermine strategic reasoning. Next, please. So the aspects of SPE, we have the sequential rationality. This concept eliminates non-credible threats, ensuring that player strategies remain consistent at every stage of the game. We have backward induction. To achieve a sub-game perfect equilibrium, players often use backward induction to drive optimal strategies from the game's end to its start. Then we have sub-game perfection. A strategy profile is SPE if it represents a Nash equilibrium of every sub-game. I said no, please, the next slide. And then you bolden it small for me. Please. Okay, application and advantages or advantages of SPE. We have ultimatum bargaining. So a proposer offers a split of a sum to a responder. If the responder is rational, they will accept any amount higher than 0, rather than rejecting and getting nothing. The SPE shows the proposer should offer the minimum possible amount. Then we have the negotiation and treaties. In labor disputes or international agreements, parties use strategies that are credible at each phase, allowing for self-enforcing agreements. One of the advantages is eliminates unrealistic and irrational strategies. Next. So we have the game tree. Please, I can't see you. Please, the game tree or extensive form provides a complete visual and mathematical description of a game. It includes players, the set of individual or firms involved, the nodes, a finite set of points, X forming a tree structure, including terminal nodes, Z, where the game ends. Actions, the possible choices available to a player at any non-terminal node. Information partition, set of nodes H and X that are indistinguishable to players moving at that point, representing what they know. Payoffs, the rewards assigned to each player at every terminal node. Game tree is applicable to the following instances: negotiation and bargaining. Okay, in labor negotiation or corporate mergers, game trees help model sequential offers and counter offers to determine the best negotiation strategy. Auction strategy. Game trees are applied to analyze bidding behavior in auctions. Example, government licenses. Predicting how opponents will react to different bidding strategies. So this is a display of our game tree. So we have the player, 1 at the top, 2 at the corner, and then it goes like that. Thank you. Next. So application of the game tree. Artificial intelligence, AI, and game theory. Strategic decision making. AI uses game tree to map out future moves and select the best one, essential for games with perfect information. Economics and business. Sequential game modeling, used to map out strategic moves in negotiations such as bargaining scenarios. So sub-game perfection. Sub-game perfection is a game theory concept that refines the Nash equilibrium, ensuring that a set of strategies forms a Nash equilibrium in every possible sub-game of a larger
morning in casa because MP the other side. My MP for the other side now we so far. Seriously.
Yo, yeah, me pacho mute kakra. So possible sub-game of a larger dynamic sequential game. And we have a Nash equilibrium is said to be sub-game perfect if and only if it's a Nash equilibrium in every sub-game of the game. A sub-game must be a well-defined game when it is considered separately. That is, it must contain an initial node and also the moves and information sets from the node on must remain in the sub-game. Backward induction. So backward induction is the process of analyzing a game from back to front. At each information set, we remove strategies that are dominated. Backward induction assumes perfect information and rational behavior, which may not always hold true in real-world scenarios. So we will show a diagram of how it works. So this is a diagram of how the backward induction works. So please, let's continue. So working from back, the pure strategy Nash equilibrium PSNE of the game is for cook. Enter accommodation, which is for cook. So that is it's in the previous slides, the diagram. So SPE and perfect Bayesian equilibrium. Subgame perfect equilibrium SPE and PBE are both solution concepts used to refine Nash equilibrium in dynamic games by eliminating non-credible threats. However, they differ primarily in the type of information structure they handle and whether they incorporate players' beliefs. So we are comparing SPE and PBE conceptually. So core purpose, both seek to identify reasonable equilibria where players act optimally at every stage of the game. Information structure, SPE works best in game of perfect information, where every decision node is a single thing. No uncertainty about the history of play. PBE, designed for games of incomplete or imperfect information, where players may not know the previous moves of others or the type of other player. Belief system, SPE does not formally require belief system. It uses backward induction on proper subgames. PBE explicitly include a belief system, a probability distribution over nodes within information sets, and requires that these beliefs are updated using Bayes' rule whenever possible. So these are our references where we got our materials from. So thank you, Ram.
Okay, Grace, thank you so much. Um, I think my first question is, did you guys really understood what you put on the slide? Do you understand all that you had said?
Not for me,
Hello,
not
madam.
100%. At least
Yes,
okay.
yes.
Me,
To
not
some extent.
100%. At least to some extent, not 100%. I won't
So,
lie.
Grace, if you've asked to, give a presentation, of course, you come up and give the presentation as though you are an expert in the area, isn't it? Because that's why we are all being trained here. That at the end of the day, if you are called to give a presentation on any topic whatsoever, you own the topic, right? So you are the one teaching us, you are the one telling us that this is what you have found. This is with your little research, this is what you did, this is what you have found. You can't present something that you don't really understand. So somebody was saying something. I don't know whether it was uh, is it Inusa? Is the name Inusa?
It was
Please.
Enoch.
Enoch, right? Somebody was saying something. Enoch, I'm listening.
No, madam, you asked if we truly understood what we
Okay,
presented.
okay.
I said,
So is it Isaac? Isaac,
Yes, Doc.
yes, what's your response to that question? Whether you really understood what you just presented?
Doc, I'm not part of the group. Okay, I mean, from what they said.
Isaac,
Yes,
no.
Doc.
Oh, Not I mean the Isaac in Grace's group.
Yes.
Doc,
Okay. Yes.
Doc, I'm here.
Okay, so Isaac, did you really understand the areas that you looked at?
Doc, not all the areas.
Okay. What about Enoch?
Hello, madam.
Yes.
Okay, so I understood aspects of it.
So how come you guys were not able to how many are you? 1, 2, 3, 4, 5. 5 people. So you could have decided to pick an aspect each, right? And then own it. You research on that particular area. So, assuming you are the one doing something on extensive form of games, you come and then present on extensive form of games, and then you leave the other one to the other person so that you own the topic and you really understand the topic that you have just, discussed.
Hello, madam.
Yes.
Eric, I'm also a member of the group.
Okay, Eric,
So
I'm listening.
on our during the presentation, what I did was to work on the backward induction, trying to understand with the sub game. So I thought maybe when questions comes, maybe we have individuals who have done research on 1 or 2 areas which we can respond to. But on that area like sub game and backward induction, I did a lot of work there. So
Okay, so let's go to backward induction. So guys, I think there was a slide, I don't know, go to slide 8 and let me see. No, move further. No, keep going. I think there was something on the bucket. Yes. Okay, so it's
So
okay.
basically, what we are trying to explain here is that we are looking at how to use backward induction to analyze a game theory. So we
Okay.
are looking at a market where Pepsi is it's already in the market. Coke decides to enter the market.
Okay.
So the game point starts with the decision point for Coke is here. If he decides to not to enter the market, its return to be 0, and Pepsi will get 5 profit. If Coke's, because it's a sequential game where information is available to everybody. So when Coke enter the market, Pepsi now decides Coke is in. What does he want to do? If he accommodates Coke by trying to cooperate with Coke, then Pepsi will get a payoff of 2, and Coke will get a payoff of 1. But if he decides to fight back, then if Pepsi decides to fight back, then Coke will also take a decision, either to also fight back or accommodate. If Coke accommodates, then the first one is Coke will get a -3 and Pepsi will get 1. If he decides
So
to
how
fight,
does
from the backward induction, we are looking at starting from the back. So we pick a sub game of Coke and Tough and accommodation at the end. Looking at Coke at that point, that sub game, the Nash equilibrium for Coke will be -3 and 1. They're trying to accommodate. Then when it comes to Pepsi for the second point, so we are looking at accommodating for Coke, which is the outcome of -3 and 1. Then come to Pepsi. Pepsi will look at -3 and 1, then 1 and 2. Pepsi realized that when he also accommodates, 1 is bigger than Pepsi know that 2 is bigger than 1. So Pepsi will accommodate. So 1 and 2 will be okay for Pepsi. Then when it comes, so we realize that
do you have the metrics for this game?
yes, but it's somewhere. So because
It's somewhere. Where is it?
Yeah. So we want us to put the metrics in the
You see, that would have helped greatly.
Okay.
As far as your explanations are concerned. People are not used to this form of presentation. I hope you understand.
Yes,
So
madam.
when you present the matrix form, right? So we present a matrix form where we have Coke maybe in the row and then Pepsi in the column, right? And then you have, so this game, one way or the other, is you have that extensive form of game. You have a sub game in it, right? The first point of the game, you mentioned that one of the companies is already in the market, isn't it? So if one of the companies, being a Coke, I don't know whether it's Coke that is in the market already. You said something like that. So you said that company is already in the market, and the other person is thinking whether or not to move into the market. So you are thinking whether or not Pepsi is thinking whether or not to enter that market that Coke is already in. And we all know Coke and Pepsi, isn't it? They are substitutes, right? So it's either people drink Coke or they drink Pepsi. So if Pepsi is entering the market, obviously it means they are going to compete, right? So the strategies in this game is what? Either accommodating or doing what? Being tough, isn't it? So you have two strategies. So you see, my point is that we have already learned some of these the elements in the game and all that. So you have to let the audience understand where we are coming from. Because if you show this, I'm sure most of us have no idea what this is about. But on top of my mind, this is a game of two firms, right? So you have two firms. You have Coke and then Pepsi, right? And then the strategies in here will be accommodating or being tough. So if you are looking at the entire game, then it means that we have two sets of strategies for one of the firms, whether to enter or not enter. So after the firm has decided to enter, then we play the game again, isn't it? Because if the other firm decides not to enter, then the payoffs in this one is 0 for the one who failed to enter, and then 5 for the existing firm. Okay, so if Coke decides not to enter, then it means that Pepsi has what? Five, and Coke doesn't have anything, right? So that is the first aspect of the game. Because it's an extensive form of a game, then it means that after there is an entry, right? After there is an entry, what happens? After there is an entry, now the strategy is that you either accommodate or you be tough. That's what all this game is talking about. So this is where you have to draw people's mind to before you start talking about the processes that you are looking at. I don't know why I'm going about explaining this when you are the ones presenting. So so my first question is that, assuming that in this particular game, what will be, do we have a Nash equilibrium? Do we have a Nash equilibrium in this game? And if there is, what would that be?
So the Nash equilibrium for this game is for Coke to enter and accommodate. That is we are looking at the first point. So you enter, then accommodate Pepsi, so that at least you get a return of 1. That is from when we analyze the game. That is a Nash equilibrium.
Okay.
Yeah.
All right, guys. Any question for group 1? Is it that you two didn't understand? Is it that you two didn't understand? And so you don't want to ask any question because you have no idea what they are even talking about, or you really, really don't have any question. Evans,
Hello, dog.
Yes, what's your question for group 1?
Madam, we are group 6.
Group 6, right? Oh, sorry about that. Group 6.
I think we should give them opportunity to present again.
We should give them opportunity to do what?
Present again.
Why? Evans, they will
I
present
didn't get.
again after you have presented yours.
I didn't get the concept.
If you didn't get the concept, then you are trying to say that all that they said you didn't understand.
Yes, please.
Okay. So guys, I've sent the scores, the forms to the class reps, so you can score the various groups, unless you.
So, Doc, on the scoring, are we scoring individually or we are scoring as a group? Hello.
It just so happened that it would have been best if we heard everybody's voice. Okay, so you can score the.
So, Evans, I want to understand which portion of the presentation you don't understand. You don't understand the backward induction, or which aspect of the presentation you didn't understand? Evans.
I think we have to make progress.
Perhaps
the presentation was read to us. I don't think that is. It's just you read the whole thing to us without much explanation. But I think we can do the scoring and move on. So, Doc, the scoring
I
is
agree.
it? Would
I
it
think we
be?
have to move on.
Would it be individually or group?
No, so if you look at the form, you realize that it's in group. So you score the group.
Okay, thank you very much.
No. So what we mean is, are we like group 1? Group 1 will score as 1.
No. If you check the Google form, you have your name. So your name is there, your index number, and then your score for the group.
Okay.
So guys, that is not to say that what people are going to, or how people are going to score you, will be the same thing that you get. I mean, it's just a test case, okay? I'm just using it to help with whatever the whole assessment process. But I will score you at the end of the day, so it's not a problem.
Madam, thank you very much.
Okay, so can we have the next group, please? Sorry, before the next group comes in, does anybody in the group have something to say?
Oh, please.
Okay. All right. So nothing from Eric 1 and Eric 2. Eric was the first person to join this call. When I joined, I think it was only the host that was on it, and then Eric joined. Eric, how come you don't have anything to say?
Is it Eric Odro or Eric Ajiman?
Which of you came earlier? I suspect it's Eric Ajiman.
Oh, okay.
Okay. If we are okay, maybe you can stop sharing and then the next group will.
Doc, please, should group 1 present now?
In group 1, sure, go ahead.
Okay, thank you.
So quickly, before you present, guys, the best thing to do is that you write the various scores on a paper, right? So maybe group 1, you are giving them this, and you are scoring out of a 10, okay? So you are scoring out of a 10. You would group 1, you write the score, group 2, you write the score, group 3, you write the score, and so on and so forth. When you are done, you put everything in the Google form and then submit. Okay. Priscilla, please go ahead.
Yes, please go. Thank you. So, good day, everyone. This is group 1, and we have also a similar question to that of group 6. And so we are here to present on the extensive form games and sub-game perfect equilibrium. Our presentation will take this outline. We'll just give a brief introduction into the topic. We'll also talk about what extensive form games are. We'll talk about the game tree example. We'll also talk about the sub-game perfect equilibrium. We'll solve one scenario question on the sub-game perfect equilibrium. We'll take you through how it's being done. And then we'll give you some key differences between the Nash equilibrium versus the sub-game perfect equilibrium so that you can do some better predictions. So, as I said earlier, we'll be talking about the extensive form games and then the sub-game perfect equilibrium, which Group 6 has also talked about, but would also present on it. So our presentation, we kind of streamlined it to focus on 3 main ideas. We are looking at the sequential decision making. We are also looking at the strategic game trees, sorry. And we're also looking at the equilibrium refinement. So you may ask, what is the sequential decision making? What is it about? What does it say? When we talk about the sequential decision making, we are talking about where players make decisions one after another rather than at the same time. And then when we talk about strategic game trees, we are actually going to use diagrams. So I think we saw it with the other presentation. We are going to use diagrams to show how decisions are made and would unfold it one step after the other. And then we'll talk about the equilibrium refinement, which particularly is the concept of the sub-game perfect equilibrium, which help us to identify the most rational outcomes in this sequential games. That is the games where the players make the decision one after the other, not at the same time. So it's like the decision is based on what the first player decides on, and then the next player will know whether to play this or that. So at least as we go on, we would explain further. So now I want to tell you what the extensive form game is. When we talk about the extensive form game, it's a way of representing strategic situations where decisions happen sequentially. Meaning, as I said earlier, one player moves after another. So instead of what we've been doing in class all along with our games theory, where you have the table with the normal games, in this one, we actually represent it with the extensive form games. We actually represent it like a game tree. Like we'll show you a picture as we go on. I believe we saw it with the other presentation. So it's like a game tree, like a family tree kind of thing. So you see it there and there. And the structure clearly shows who moves first and then who moves next, and what choices are available at each stage. And there are 3 main components, like what we learned earlier in class. We have the players, which are either the individuals or the firms making the decision. We also have the actions, which are the choices available for each player. And we also have the payoffs, which is the outcome or rewards each player receives at the end. So you can think of it as like a decision tree, where every branch will represent a choice and every endpoint will represent the final outcome. And so, as I said, we'll show you a visual structure as we go on to help you understand it better. So this is an example. On your right-hand side, you can see we have visualized the game tree. We've actually turned it, but you can also turn it the other way. I don't even know how to explain it. The P can be at the top and then the others will follow. It's still the same game tree example. So let's take a look at this one. So this is a simple example of a sequential game tree. And from here, just imagine that there is a new startup firm, a firm who wants to enter the market. For instance, let's say the firm wants to enter a market there's an already existing firm. So let me liken it to maybe a stationery. There's an already existing stationery firm, and let's call that stationery firm incumbent. And then there's a new startup player who we can say is just a startup. So the new startup player, let's name it P1, which is the player one. Now, player one wants to actually enter the market, but then player one is in a fix. Should I enter or should I just stay out because incumbent, which is the existing firm, is doing so well? And so player one has two decisions to make: to enter the market or to stay out. And if player one decides to enter the market, so now player two is just watching carefully in a way, quote unquote. So if player one decides to enter the market, player two would have to come up with a strategy or have to make a decision. If it stays out, it stayed out. Player two doesn't have to do anything. But then you realize that if player one stays out of the market, player one would have a payoff of 1, and then player 2 would have a payoff of 3. I think we remember the arrangement as Dr. Afarebea taught us the other day. So the first one is for player 1, that's 1, and then the 3 is for player 2, which is the incumbent one. So if they stay out, these are their playoffs. But if they decide to enter, that's if player 1 decides to enter, then player 2 would have to come up with a strategy. And player 2 would come up with a strategy whether to fight player 1 or to accommodate player 1. Now, from the presentation here, we can see the knots. The knots actually represent the decision points. Unfortunately, I don't have a pointer, so I'm not able to show. And then the arrows represent the possible outcome or the possible actions. So you can see the arrow here to enter and then not stay out. And then, so if player 2 decides to fight, okay, player 1, the payoffs would be 0-0. I mean, they both gain nothing. But then if player 2 decides to accommodate player 1, then you realize that the payoffs is 2-1. So that means player 1 would benefit, will get a payoff of 2, and then player 2 gets a payoff of 1. Now, when we look at it, 1 is greater than the 0. So it would be better for player 2 to accommodate than to fight, than to gain nothing. And then when we come to, I believe my colleague, Prince, is online. He also continued. But then I just want to give you a fair idea. I believe so far we are getting it. So player 1, 2, from the initial one that we did stay out and enter, you realize that when they stay out, they are getting 1, a payoff of 1. But if they should enter and then they are accommodated, they are getting a payoff of 2, which 2 is greater than 1. And it's rational that player 2 would rather accommodate than to fight. But please, at this point, let me hand over to my colleague who will take over from giving us more insight into what the sub-game perfect equilibrium is, the backward induction, and then explain this further for our better understanding. Bring over to you. Thank you.
Okay, Priscilla, thank you. Let's move on to slide 4. Okay, slide 4. Sub-game perfect equilibrium. Now we introduce the key concept of our presentation. That's the sub-game perfect equilibrium, or the SPE. Formally, a sub-game perfect equilibrium is a strategy profile that is a Nash equilibrium in every sub-game of the original game. In a simpler term, this means that players must make the best possible decisions at every stage of the game, not just at the beginning. Why do we need this concept? First, normally, Nash equilibrium can sometimes include threats that are not believable. For example, a player might threaten to take an action that would actually harm them if the situation really occurred. Sometimes SPE requires substantial rationality, meaning players behave optional at every decision point. Because of this, sub-game perfect equilibrium refines Nash equilibrium, giving us more realistic predictions. In short,
I get it.
SPE ensures that players only make credible strategies that they would actually carry out. Slide 5. Solving for SPE backward induction. To find the sub-game perfect equilibrium, we use a method called backward induction. The idea is simple. We start from the end of the game and work backwards to the beginning.
Okay, but what to Nani?
First, we look at the last decision, which belongs to player 2. Player 2 chooses between fights, which gives payoffs of 0-0, or accommodates, which gives 2-1. Since player 2 gets 1 instead of 0, the rational choice is accommodate. Next, we move backwards to player 1's decision. Player 1 now anticipates that if they enter the market, player 2 will accommodate. So if player 1 enters, they receive 2. If player 1 stays out, they receive 1. Because because 2 is greater than 1, player 1 chooses to enter. Therefore, sub-game perfect equilibrium strategy is player 1 chooses enter, player 2 chooses accommodate, and final outcome is enter and accommodate with playoffs of 2-1. Slide 6. Nash equilibrium versus sub-game perfect equilibrium. Finally, let's compare with Nash equilibrium and sub-game perfect equilibrium. A Nash equilibrium simple requires that each player's strategy is the best response to the other. However, it may include non-credible threats, meaning actions that players would not realistically carry out. Sub-game perfect equilibrium is stricter, very strict. It requires that strategies are optional, strategies are optimal in every sub-game, ensuring that all decisions are credible and rational. In our example, several Nash equilibrium might exist, such as enter or fight, stay out or fight. However, when we apply sub-game perfect equilibrium, only one outcome survives: enter and accommodate. This is why SPE is important. It removes unrealistic outcomes and provide more reliable predictions in subsequent games. In conclusion, extensive extensive form games help us understand strategies decision making over time. Sub game perfect equilibrium ensure that the strategies we predict are credible, rational, and realistic. Thank you.
Hello.
Hello.
Hi. Forgive me. I'm sorry.
Madam, you are lost.
I was. Excuse me, bro. Okay. So thank you so much. Book one, right? I think I think um I mean some of the concepts are a bit clearer. Um let me see if Evans. Evans.
Hello, dog.
So are the concepts clearer? Do you understand them now? Because it's the same presentation. I mean, not the same presentation, but I mean the same idea.
Yes, please.
Okay. Okay, so guys, I thank you so much. Anybody from the group to ask a question? I think the game that they presented is almost the same as the game that the initial group presented, right? I mean, it's the same concept, obviously, because the topics are the same. So at the end of the day, we need to um, think through this. A game where there is an existing firm already in the market. Now one wants to enter. The issue is that the first decision is whether or not the second needs to enter or not. Then the second, after they've entered, then what happens? After they've entered, then we have to start with another strategy, whether we should accommodate or we should fight them. Okay. I'm sure we all know about the Cola Wars. I don't know if you are aware, but if you don't know about the Cola Wars, maybe if you Google, you would have Cola Wars normally is looking at the fight between Pepsi and Coca-Cola. If you look at their adverts, if you look at their adverts, if you look at even sometimes the campaigns that they, bring out, you'd realize that it's like a fight between these two companies. So this particular game that the two presenters are talking about are looking at where we have instances like that. So assuming a market where there is only one of these companies in there and just one company there, and then the other wants to join. Now the decision is whether or not, after joining, whether or not they should accommodate or they should fight. So the payoffs are what has been indicated. And at the end of the day, if you are looking at the backward, you look at the various payoffs at the end of the game tree. Okay. Now, one thing that I wanted to mention is that all the games, I think I mentioned it in the previous class. I said all the games that we had played, all the games we had played can be presented in a tree form, right? So you can present those games in a tree with the notes and all that, indicating where we have the information set, where we have the action that the person is taking. You already understand what the action is, and the action stems from the set of strategies. I already explained what the set of strategies entails. So at the end of the day, if you are looking at the backward induction, you are looking at situations where you are solving the game from the back, okay, at the end. So if you look at where they had presented the tree, they mentioned a particular solution. And that solution was because they compared for one of the companies which is the best to do. We've been doing this in the matrix form, okay? If you would recall, I think last week when we met in class, we did something similar. So we've been doing it in a matrix form. The same thing, since the same game can be presented in a tree form, and obviously, when you are looking at the extensive form of games, it's even best to present it in a tree form, because for the extensive form of games, what happens is that you have one set being played. At the end of the day, you are playing another set and all that. So the tree can be extended like the branches. You have tentacles all over. So you can go on and on and on. Okay. So if you look at the end of the game, what will be the result? Based on that, we take the decision. And that is how they were trying to explain that of the backward. Guys, if you have any question whatsoever, you can throw it to the team and then we proceed to the next team. I'm not too sure we'll be able to finish with all the teams today. In actual fact, I wish we could end everything today. But how many meetings do we have? How many meetings do we have next after this class?
Three meetings also. Yeah.
3 meetings. Okay, so I mean 3 meetings without the revision, right?
Yes.
Okay, then that's perfect. So I mean, if we are unable to conclude today, we'll be able to conclude that next week because we have 2 meetings for the incentive. Was it for the design, right? So at the end of the day, let's be fast about it, but if we are not able to finish next week, we'll continue. So group 2, sorry. Group 2, if you are not sure. Okay, so Savior's group.
Hello? Hello?
Yes. Yes,
Hello.
Savior. So please
Good,
let's try to be fast, a little bit fast about it. Okay.
okay.
All right.
Good
Thank you.
afternoon, everyone. This is Inusa. I'm here to present on behalf of Group 2. I will start with a presentation and along the line. A team member will take it from there. So, first of all, I would like to read out our requirements or what we were supposed to do. So, we're supposed to define sequential rationality and then also to identify all information sets as well as compare SPE and perfect Bayesian equilibrium, that's conceptually, and also to apply to a case study to give it a proper understanding. So let me move to slide 1. Okay. Please, can you see the first slide? Sorry. Hello?
Yes, we can,
Yes,
but can
can you
you
see
put
the
it in
first
a
slide?
presentation mode?
Okay, let me do that quickly. Mm,
Thank you.
Okay. All right. So, as I earlier on indicated, we are supposed to give explanation to sequential rationality. And as we've displayed here, so we've done a brief, and I will be speaking to that accordingly. Sorry, I have kind of lost my voice, so I would have to indulge me. Yes, so in a standard Nash equilibrium, we only require that a player strategy be optimal, at the very beginning of the game. However, in a sequential interaction, this can lead to unreasonable outcomes, right? So we are saying that a player strategy must be optimal at every decision node during the game, not just the start of it, right? And the key requirement is that you choose an action that maximizes utility at every node, given beliefs and opponent strategy. So you take into account of these 2 things, right? So in sequential rationality, we take it as a requirement that requires a player to act optimally at every point um, during the game, not just the beginning. And this means that if a certain stage of the game is reached, the player must choose an action, right, that maximizes their utility based on their current belief. If new information arrives, then they must modify or they must change, those beliefs according to the law, right? And this means that they are acting rationally, because if new information has arrived, there's no need to hold on to the old beliefs. You have to modify accordingly. Essentially, sequential rationality is a tool that we use to filter out the equilibrium, that relies on threats of a player that would never actually carry out when the time comes. Right. So this is a brief explanation of the sequential rationality as we were asked to. So I'll move on to the next requirement, which has to do with identification of information sets. And from there, take it. So the next one has to do with identify information sets. Right. So to understand how players make rational choices, we must also um, define their information set, right? So, per our research and per our readings, an information set is a collection of all nodes in the game tree, right? And I think the first speaker did even show a graphic of how a game tree looks like, right? So, in their context. So, the collection of all nodes in a game tree that a player cannot differentiate between when it is their turn to move, right? So we have the perfect information and then the imperfect information. So with the perfect information, if an information set consists of a single node, the game is one of a perfect information, right? The player knows exactly where they are and what has to happen, sorry, what has happened previously, right? So that is for the perfect information set. For the imperfect, if the player cannot distinguish between the multiple nodes, right? Oftentimes it depicts that there's a dash line in the game tree. And sorry, we don't have a picture to show in this slide, but it has to be taken down for now. So the game has imperfect information. That's how we take it for. And this is typically um, in a situation where choices are made simultaneously, or where a player is unaware of the opponent's specific action or prior action in that regard. So that is for the perfect, and then the imperfect. I've done some briefs here. So when you look at the perfect information, every information set consists of a single node. The player knows exactly where they are in the game tree. Example is the standard sequential bargaining, and then that of the imperfect. And then we move to the comparison, the comparative analysis of the SPE and the PBE. So we have the sub game perfect equilibrium, that is the SPE, originally defined by the around 1965, that we've researched. And as equilibrium is a sub game perfect if it constitutes a Nash equilibrium in every sub game of the original game, right? So we identify these using the backward induction, as the second group explained with their backward induction, so we reason from the final move of the game back to the start, crossing out inferior options at every stage, right? So, and when you look at the perfect Bayesian equilibrium as well, so the PBE, it also look at how it works well. So basically, it works well for games of perfect information, right? So it is used for games of incomplete information, where we know that players may not know the type or the payoff of their opponent, right? So in a PBE, the players maintain some sort of probability, or like probabilistic beliefs about these types, and update their beliefs as they gain information, right? So basically that is also that we've done some breakdown here, given the requirements as well as the rule. So, and then it's also important to take notice that beliefs must be consistent with the actual strategies in the equilibrium, right? And also with the subgame perfect equilibrium, the limitation is that it's less effective with incomplete information, right? So that is that for that. And so we have a case study here, case study of Microsoft and IBM. So we created a scenario where we have Microsoft, that's a potential entrant to a certain market. Let's assume that IBM is assuming they are monopoly in one of the markets. Let's say when it comes to hardware infrastructure, right? So you have Microsoft being the potential entrant, and they decide to enter or stay out of the market that is dominated by IBM. In this context, let's say a hardware market, because Microsoft, we know they own the Windows software, which is the most popular in the world. So Microsoft enters, and IBM can either accommodate or smash, right? So this case study that we created, I would hand over to my colleague to give a detailed explanation of the case study, and we take it from there. Thank you very much. Forsen, if you are here, you have the floor.
Okay, thank you very much, Adnan. So we would like to throw more light with respect to Microsoft and IBM, with the scenario being here that Microsoft, that is a potential entrant. Here he decides to whether enter or stay out of the market. So here he has two options here. It's either he enters the market or he stays out of the market. That is dominated by IBM. So here he entering the market or staying out. This market is already been dominated by IBM. That is the incumbent. So here he has two options. If Microsoft enter, then IBM can either accommodate or smash or at price war or just move out. So we try to give out the information set. With the information set, Microsoft will first of all try to move first at a single node information set. And then IBM might also try and then move second with full knowledge that Microsoft enter. So here, IBM is the dominant. He has dominated the market for some time now. So the two information sets here is that Microsoft trying to be the new entrant, will try to move in with a first single information node, and then for IBM to catch up with a new entrant, he will also move second with a full knowledge that Microsoft had. So here we try to, with a sequential rationality in the second diagram, we gave a diagram that explains those two. So here IBM may threaten to smash it out if Microsoft enters or not. So if he tries to enter, there are two outcomes that may come out of board. One, that is only the credible equilibrium Microsoft enters and IBM accommodates, or the threat of smashing is non-credible. That is, IBM will carry it out, so it cannot deter the entry. So the central truth of it is that the Nash equilibrium is where Microsoft stays out. He's been fearing being smashed out, or he's being rejected. The threat is non-credible. So that is the case study. I don't know if you proceed.
Yeah, so that's the end of the slides. When you look at the requirements of the question, so it was for us to end with the case study. And so we have some references here as well as the end. So this is brief. As Doc said, we have to brief about it. So we are open to questions at this point.
Okay, thank you so much. Guys, any question? What about the rest of the team? Do you have anything to add?
Yes, madam. So as I indicated earlier on, one of our team members, Josephine, she's not part of this semester, so she's out. And then we have another colleague, Xavier, and also we have information from the last person, Anthony. He informed us that he wouldn't be able to join due to some circumstances, which I'm sure he has also informed the course rep about it. So we are currently three on the call. Hello? Hello?
Yeah, hello.
Hello? Yes, am I
I can
audible?
hear you.
Oh,
Okay,
sorry.
okay.
I had muted and I was talking.
Oh,
So
okay, okay. We didn't catch that.
so sorry. It's just I mean the same way as initially I had unmuted and I was talking. Forgive me when it wasn't necessary. Okay, so forgive me for that. I said thank you very much. So we don't have Anthony and Xavier on the call, so we are only left with Ebenezer
No,
and
please,
Inessa.
I'm here.
No, so Xavier
Xavier
is
is here.
here. We don't have Anthony and Josephine.
We don't have
The ladies.
Anthony and Josephine.
Yes.
Yeah, it's
But
Anthony and Jeff.
Xavier,
Yes,
but
please. Xavier is here.
Xavier, I've not heard your voice.
Yes, please, I'm here.
Okay, okay, so say
So we are talking
something.
about the two pure strategies Nash Equilibra is. It's either they enter or they accommodate. So if the Microsoft enter, BM best response, it should be accommodate. That is
Xavier, let me spare you. Anyway, guys, if you don't have any question, I think we'll take the next group.
Okay, thank you very much.
Thank you so much. Xavier, Inusa, and Ebenezer.
Thank you, madam.
Thank you, Mana.
Okay, can we have the next group? Can we have group 2? No, group 7. Since they are presenting on the same thing. Charles.
Yes, Doc.
Charles, where is Nene?
He's around.
Okay.
Madam, please, I'm here.
Okay, so I'm waiting for you guys.
Yeah, Moses is sharing his screen.
So this is group 7, isn't it? Please, if you are saying something, you are muted.
Okay.
Okay.
So who is a Zoom user?
Moses, but Majid here to present.
Okay.
Yes. Good afternoon.
So Majid is a Zoom user.
No, Moses. Yes, I use Zoom, but Moses has shared his.
No, that's the name. I know, but that's the name showing. So I was a bit confused.
Yes. So
Okay. Please go ahead.
thank you. I'm Majid, representing Group 7, and this is the outline of our presentation. We are supposed to look at sequential rationality, information set, subgame perfect equilibrium, that's SPE, and perfect Bayesian equilibrium, that's PBE. Then we look at a case study, and in our case, we've decided to look at the current Iranian and then Israel conflict.
Okay.
Yes. So next. Moses, please, the next one. Yes. Okay. So to start with, we are looking at Moses, the first slide. Yes, we are looking at the sequential rationality, just like our previous the previous group presented. Now, basically, sequential rationality in this game, we are looking at a game where one player has to play, then the other one respond. So they don't play simultaneously, but rather in a sequential form. And they should play such that in a rational form, such that everything or every player looks at the maximum output at each point, or maximum payoff at each point of the game. So we say sequential rationality means players make the best move at each step, considering what they know and expect others to do later in the game. It's about making rational choice given the situation, looking ahead to the future consequences. So basically, based on whatever information you have, you are supposed to make a rational decision based on what the other player does. So that's sequential rationality. The next one is to look at information sets. So we are saying that information set represents the state of knowledge for a player at a specific point of the game. So basically, all the information that a player has at a particular point of a game is what we term as the information set. And when we look at the information set, we have what we call perfect information and imperfect information. Now, when you look at perfect information, this is where every player at every decision point has or know full history of the game up to that moment, that knowing whether where they, so basically with the perfect information, the player has full information or history of where they are and what um sorry, they have perfect information of they have all the information in relation to the game at that particular point in time. So they know whatever information is available. Whilst the imperfect information is a situation where the players doesn't have much information, or they don't even know where they are at a particular point in the game in order to be able to make a decision. Yes, but they must make a decision even though they don't have all the information. They still have to make decisions. That's with the imperfect information. Yes. Let's continue. So we are looking at sub-game perfect equilibrium and perfect Bayesian equilibrium. Now, we are saying that when you look at the sub-game perfect equilibrium, in the sub-perfect game equilibrium, there is information. So we say best for perfect information. We use this game where there is perfect information. Whilst with the Bayesian, it is used where there's imperfect information. There is no much information, but yet still you have to make a decision. That's when we use the Bayesian equilibrium. But with the sub game perfect equilibrium, that one you have perfect or full information or full history of your players, of the other players' moves. Secondly, we are saying that with the sub-game perfect equilibrium, they use what we call the backward induction. That is, they look at all ways the other player would respond or would play from the beginning to the end. Then they start at the end and look at, okay, these are the possible outcomes. So they start from the end of the game. Then they look at if the players to play rationally, how would he, from knowing the beginning and knowing the end, when you take the end, you can move backward, trace backwards, and know all the possible game or all the possible strategies that the other player would use. That's what we call the backwards induction. But with the Bayesian, we use what we call the Bayesian rule, or the Bayes rule plus sequential rationality, which is with that one, there's little information. So because there's little information, we have to believe that the player would act rationally, right? So instead of backward, that one you know the history of the player. That's what move the player is going to do. So you just based on the move or the history that they are going to do, even though you are not sure of where you are, and you believe in that, and then make your move. Then we are saying that with a sub game, we assume you know exactly where you are at a particular point of the game so that you can make a decision. But with the Bayesian, you have to use belief in order to handle uncertainty because you don't have perfect information. So, for instance, you don't know if your opponent is threatening to do something. You don't know if your opponent, what he's saying, is a credible threat or not. But you would use your belief based on what you know or the little information you know to make your decision. And we're also saying that with the sub game perfect equilibrium, it is just a refinement of the Nash equilibrium, where at each point in time you must look at maximum utility. Meanwhile, with the Bayesian is also a refinement of the sub game perfect equilibrium. Yes. So both of them are Nash equilibrium. However, with the Bayesian, it is a perfection of the sub game. Now, in our case study, just like we said, we are using the Iranian and then the Israel conflict. Now, please, we are not using the matrix to represent this, but just going purely the game. So we are saying there are two players. Player one is Israel, US. So basically, when we say Israel, we mean Israel, US, and then the allies. That's the other Gulf countries. And then Iran is a player two. Yes. So the next thing is what information is available, or when we are looking at the information. Now, the information set. So with the information set, we know that Israel wants a regime change. We know that both countries are believed to have nuclear capabilities. We know that all the Gulf countries are saying that they are staying neutral. And we know that both countries believe they do not want all-out war. However, there are some missing information. For instance, we don't know if so. So there are some missing information such that Iran's or Israel doesn't know if it attacks, to what extent Iran will retaliate and vice versa. So we're looking at the strategies. Israel strategy is to eliminate the nuclear threat by Iran. Now, Iran is saying they have nuclear capability. Israel, in this game, Israel knows that it will go against them if Iran has that nuclear capability. So their best strategy is to eliminate the nuclear threat of Iran and show that they are dominating the whole area or the whole region, Gulf region. Iran, knowing this, what is also their strategy? Is to call, they know that, just like I said previously, when we talk of Israel, we mean America, Israel, America, and then the other countries. So Iran knows that it doesn't have that much power as compared to Israel. So what are the best strategies it can also, because at any point in time, you have to get a best strategy. Iran knows that going all out war, what it can do, or the best strategy, is to cause what we call the global economic pain by blocking, let's say, the Strait of Hormuz to prevent oil and food from going in and out so that there will be economic pain to the whole globe. And also, by doing that, would also force all the other countries to cooperate, and then the war would stop. So that is also their best strategy. And then we looking at the payoffs. So at the end of the day, if Israel feel like, hey, whatever Iran is saying is just bluffing, they say they have nuclear capability, it's just bluffing. So let's test. And this test, in reality, just happened with what we call Operation I mean, America just launched an operation at Israel, and then
Hamas.
yeah, no, Epic Fury, sorry, Operation Epic Fury, right? So because Israel or America, let me put it, feels like when they weigh the notes, they feel like Israel, Iran is what they are saying is is a bluff. It's not a threat. It's not a real threat. So let's do Operation Fury, Epic Fury to test and see. So they launch and then they eliminate the nuclear threats. Then they also show their dominance in the area. However, Iran also would have to do get their payoff by doing things that would cause the whole globe to feel the economic pain by blocking the Horn of Hormuz, and at the same time attack any other Gulf country that helps Israel to attack them, therefore forcing them to also to forcing the other countries to cooperate with Iran so that this war will stop. So when you pick this game, generally, you'd realize that there is an equilibrium. There is a place where they all have to agree. That's if Israel doesn't attack Iran, Iran would also not retaliate. And so basically, that is our case study. And these are various references that we have for our information. Thank you very much.
Okay, thank you very much, Nene and Moses and Mustafa. Is Mustafa there? Charles.
Yes, madam, I'm here. Good evening.
Charles, Majid. I think that's it, right?
Yes, please.
Okay, so thank you so much. So I really appreciate the fact that you had included a recent, issue. What I wasn't so clear about was the payoffs as far as these issues were concerned. If you could have put some utilities at the end of it and had shown us a combination of the strategies that were going to really maximize their, I mean, not necessarily putting, um, like real payoffs there, but maybe you could have just thought of some utilities at the end of the day. These are not payoffs, in actual fact. These are not payoffs. These are more or less like strategies. Okay, so these are strategies.
Yes, madam.
So the payoffs, I'm talking about the utilities at the end of whatever action that they take. So after everything, how will that benefit them? You get it? So if we could have,
Madam,
Well noted, madam. I think when Majid was present, he said he said it, but just I wasn't on the slide though, which
yes,
is
so
all accepted.
but after everything of course, Israel may be able to eliminate any nuclear threat. So after everything, that may be a payoff for them if they are able to achieve that.
so I don't think you really understood my point. So I'm saying that these are the actions, right, that they are going to take at the end of the day. But after taking that action, how will it benefit you? What will you gain from it? You understand? That is the payoff. At the end of the day, what do you get?
Yeah, madam.
Do you achieve happiness by this? Do you achieve, I mean, how will that benefit you? You understand? These are the actual payoffs that we are looking at. So, I mean, in economics, as far as the payoffs are concerned, we are thinking of utilities, we are thinking of profits. I hope you understand what I'm trying to say.
Yes,
it's
madam.
well noted, madam.
Please, madam. Would that then mean that, for instance, with our pay of 1 for Israel, saying that elimination of nuclear threats, which is one of the things that would make them feel more comfortable, which is the utility.
After you have eliminated the nuclear threats, feeling comfortable. What,
Oh,
how,
okay, okay,
by,
okay.
by what margin? Like, how will that, how will you feel that comfortable? And comfortable, how are you measuring that comfort?
Yes, doc, that's where we had a problem because we didn't know how to measure. You see, most of the things in
Exactly.
our
I
scenario
mean,
were not able to be measured. So
exactly.
we had to just put in the scenario. That's why.
Exactly. So my point here is that sometimes, which is why if you are looking at some of these things, alternatively, you could use like functions, right? So if you would recall last week, we did functions as far as these payoffs are concerned, where we're looking at the Kono and the Bertrand and all that. So at the end of the day, what will be the person's payoff? And we were looking at functions in relation to profit. You get it? We didn't actually get an exact value for the profit, but we used functions. I mean, it will be difficult for you at this stage. It means you'll be doing measurements. You
Yeah.
understand my point? But I'm
Yes, please.
saying that what you have put out here might not necessarily be payoffs in itself.
Yes, please.
I hope you
Yes,
understand
please.
what I'm trying to say.
Yes,
Yes,
please.
please.
They
Sorry,
might not be, they might not be the payoffs in itself.
the
They
real
are
payoff. Yes.
strategies. Okay, so if you
Yes.
had even put numbers that assuming that they eliminate the nuclear threats and whatever, this is how much satisfied they will be. And assuming Iran had caused global economic pain, this is how much satisfied they will be. Even if you had put it in a function form, you get it. So
Yes.
maybe it will give them a distance of maybe x squared or this. And then at the end of the day, you say that if x is greater than this, or if this is greater than that, then it means that they are going to choose this. So the equilibrium will be that. And that's what we do in economics. I hope you
Yes,
understand
madam.
what I mean. Aha.
Yes, please.
Yes, please.
Aha. So if it is this is what you have. But I really, really appreciate the fact that you had come up with, I mean, it's pretty innovative. Thank you.
Thank you very much.
You're welcome, madam.
Thank
All
you.
right.
Thank
So
you
can
very
we have
much.
the next group? I think we still have some time.
Good evening, madam. Hello?
Yeah, we can hear you.
Yes, yes, please.
Yes, sir.
This is
I'm
group.
sorry. I was just talking to myself. Is it group 3, please?
Yes, please. Group 3.
Okay.
So, Ken, please.
This is who is speaking now? You said Ken?
Yeah. So Isaac is speaking now. Ken will start for us.
Okay, Ken is starting. All right. Is Ken in group 3?
So, that's Ken, baby.
Okay. Joseph. Ken is Joseph. Okay.
Good afternoon.
Ken, what are you using two English names for? Okay, go ahead.
Good afternoon.
Is that Ken Kennedy or it's Kenneth?
Kenneth.
Kenneth, okay. Go ahead.
Yes. So my name is Joseph Kenante. We are group 3. And
Okay.
we are presenting on the Isaac, if you can show the we are presenting on repeated games where we are considering an infinitely repeated business dilemma. And then A, we are deriving the condition under which operation can be sustained using the Grimm trigger strategies. B, explain the role of the discount factor. C, interpret the Fook theorem. And then D, apply to the cartel stability.
Yours is really loaded, eh?
No.
So in an infinitely repeated prisoner dilemma, players interact repeatedly over time. And we are saying that under Grim trigger strategy, when one player cooperates, it's at an initial stage, if one player cooperates and then another player also cooperates, the cooperation continues for a certain time. And after a certain time, if one defects, if one cooperates and another one defects, the defect affects the other one infinitely or completely, which means that if firm A and firm B are cooperating at the same time, the cooperation continues. But the moment one firm defects, it affects the other firm forever. And then we are also saying that, so if a player defects once, the other defects forever. And the cooperation is sustained when the data. So we apply a discount factor, where the discount factor is a symbol of the data. So we are saying that the data, when the discount factor is greater or equal to, we are representing T as the temptation payoff, and then R the reward for cooperation, P is equal to punishment for the payoff, and then S is representing the success payoff, and then the data is equal to the discount factor. So cooperation is sustainable when the discount factor is greater or equal to, into bracket, the temptation payoff minus the reward for cooperation, or divided by temptation minus the punishment payoffs. And these are our matrices. So player A cooperates. When player A cooperates and player B cooperates, they all get a reward, which is the RR. When player A defects and player B cooperates, player A gets temptation payoff, and then player B get a success payoff. In the same manner, if player B defects and player A cooperates, player A gets a temptation payoff and player B get punishment. Isaac, if you can go to the next slide. If both cooperate forever, so the PV is the previous value, which is a cooperation. So the PV is the previous value. If the PV is equal to reward plus the discount factor, or multiplied by multiplying the reward plus another discount factor multiplied by the reward, and you continue like that, we have the PV, which is the cooperation, is equal to the reward divided by 1 minus the discount factor, or into brackets. If player A, if player defects while the opponent uses Grim trigger, it gets T today, which is the temptation today, then P, then punishment forever after. If at this point, if you cannot get anything, you can just draw my attention so that I go over. So if a player defects while opponent uses a Grim trigger, it gets a T today, which the T is the temptation, then punishment forever. Then the previous value, which is the defect, is equal to temptation plus the discounted factor, multiplying the punishment plus another discounted factor multiplied by the punishment. So the data, which is the discounted factor, the discounted factor is the amount of measurement, or let's say the satisfaction that you will get from A will get in the future, as compared to the payoff or the utility that you will get currently. So if firm A sees that the payoff or the reward that you will get now is bigger than the reward that you get in the future, it will defect. So we say that where delta is called the discount factor. So cooperation is sustainable if the previous value, which is the corporate, is greater than equal to the previous value, which is the defect. So if the payoff in the future is higher than the payoff currently, it means that it will defect instead of the corporate. So we solve for the formulas. So at the end of the day, we have the final condition. So we have a discount factor is equal to is greater than or equal to into bracket temptation minus the reward into bracket, or is divided by temptation minus punishment. As the previous next slide. I think I've explained this part. So we are saying that players focus on short-term gains, and then defect becomes more likely. So let me hand over to my next colleague so that he continue from the next slides. Thank you. That is the Folk theorem.
Okay.
I should continue.
No. I can go ahead.
Okay.
Okay, so we are talking about the interpretation of the Folk theorem. And with the interpretation, the Folk theorem itself is defined as an infinitely repeated game with many outcomes that can be sustained as Nash equilibrium if players are sufficiently patient. So realize that if players are sufficiently patient, the discount factor is high. And any feasible payoff that gives each player more than their minimax payoff can be sustained as a Nash equilibrium. And the key idea behind the Folk theorem is a repeated interaction allows punishment strategy. And this includes the cooperative ones. And with the cooperative outcomes become possible even if the one-shot game predicts effects. And with this, when players can enforce cooperation through punishment strategies, like the Graham triggered strategy, the equilibrium outcome is not limited to the state game. That's the Nash equilibrium. Please move to the next slide. So we have our matrix here for player A and player B. So you realize that if player A cooperates and player B also cooperates, there's a mutual reward. If player A cooperates but player B defects, that's a so this matrices we have a payoff. So you can see on your right side down there that we have payoff, the key payoffs for player A and player B. So the 5 is a temptation where defect while other cooperates. So the temptation may be either player 1 defecting and the other cooperating, or player B cooperating, or player B cooperating and player A defecting. So that's the temptation. So the 3 is the reward. That's where both cooperate. And 1 is the punishment where both defect. And 0 is Saka, where cooperate while other defect. So it could be for both players.
So we realize that with player A, if player A cooperates and player B also cooperates, we have a mutual reward. But when in a case where player A cooperates but player B defects, that's where the success payoff comes in. In a situation whereby player A defects but player B cooperates, we have temptation over there. And in a situation where player A defects and player B also defects, that's where they both defect and there's a punishment. So we can interpret it in an economic setting. So in a single short game like this, the yellow cell is the only logical outcome. So the yellow cell, that's cell 1-1, is a logical outcome. And if you are to ask to choose the Nash equilibrium, that would be our Nash equilibrium. But however, the Fock theorem suggests that in an infinite timeline, players move to the top left, that's the 3-3, to maximize their long-term gains. So Fock theorem is trying to let us know that the game is infinite. So they can, in the long term, they can move ahead more to maximize their long-term gain. So I'll end here for my other colleague to continue. Thank you.
So yeah, my the presentation flow. So Ken Fred will continue.
Ken. Hello, Ken.
Hello, Doug.
Yes,
Doug,
I think
I think King Fred is not around, so let me continue from there.
Okay.
Yeah, King Fred is not around. So this is Ken Joseph Nante. So
I'm trying to share the screen again. I don't know why it's not coming.
So that we are applying to the cartel stability. So the cartel stability is simply just it's an agreement between two firms. It's an agreement between two firms where the two firms agree that okay, we are we are setting price at this level. Either we are setting price at a higher, so that we all gain profitability, or we are restricting output or production in the market for able to get or gain or get a market share. So the cartel is just an agreement between two firms or maybe two countries. Where in the real life, let's apply to in the real life, let's say Ghana is having a bilateral agreement between China, where they are deciding that okay, they are removing some tariff restriction on certain imported and exported goods. So this is an agreement between the two countries. But where one country decide that, let's say Ghana decide that they are based on the agreement that they had, that they are putting restriction on some tariff on some certain items. But later Ghana decided to hold or let defect that agreement. Then it means that Ghana's relationship with the or other countries or China's country, the relationship in the long run, it will affect Ghana in the sense that when you have a bilateral agreement and you decided to defect, in the long run, it will affect your import and export from other countries. Because the other country can also decide that, okay, once you have defended that agreement, we are also putting or holding a restriction or putting high tariffs on our imported or exported goods, which in the long run will affect the other country. So that's the cartel stability, just an agreement between two parties or two firms where they set high price to gain market share, or they set a target for a production or output for them to be able to get a market share. Thank you.
Okay, so guys, thank you so much. And I really think that we have picked a thing or two from this particular presentation. I was thinking that Esther, I don't know if you'll see the topic that you had done being maybe if we should talk about real life experience, whether or not you can think of either relationships, marriage, etc., right? So I think when we met face to face, I was talking about some of these things. And as far as the prisoner's dilemma is concerned, you recall that I said if they are to cooperate, what will happen? It means that the jail term will be lesser than each of them confessing. Do you remember that? So if both of them should cooperate, then the returns will be you know, um, the payoffs will be better as compared to they confessing. However, in a one-time game where they just played once, the best thing to do is to what? Confess, because you know that um, the dominant strategy for the first prisoner is to confess, and the dominant strategy for the second prisoner is also to confess. But this particular theorem is telling us that in a game where we keep on repeating, so where we are, going on and on and on, it's like we have an infinite kind of agreement. So at the end of the day, we agree that, Charlie, let me not go and say anything, right? And so if they catch us, we just spend 6 months and we are out. If they catch us, we just spend 6 months and we are out. So almost every time you go and steal, they catch you, you get 6 months, you're out. You steal, you get 6 months, you're out. If one time one person tell on the other and says that, oh yes, we went to steal, and the person is out, and the other partner stays in the prison for some time, the likelihood is that when it happens again, the other person is also going to tell on the other party is high. So this is what happens. If one person sort of decides not to cooperate at even one point in time, there's going to be a punishment, okay? Which is why I was asking you whether you see this to be a game even being played in real life experiences, including marriages, where in marriages you guys are trying to be together. You don't want to, cheat on the other partner. You are together, you do everything together. If one time the other person decides to cheat, you would see that subsequently it breaks the trust, right? And so you don't trust the person again, that the person is not going to do. So, I mean, things change. Things will never be the same. So basically, that is what this whole theory is looking at. And I really appreciate the example that you gave. Just that the cartel bit is what you didn't really, I mean, you explained it, but I really wish that you would, it's just as I had mentioned. So two firms in a market, in most cases, if they should collaborate, they would reap better profits, right? Because it's just these firms in the market. Assuming these are the only people that produce, even water, right? Assuming water, they decide that, oh, we are selling water for 3 Ghana cedis, irrespective. So that's 3 Ghana cedis for every brand of water that you go and buy. Okay. At the end of the day, they will share the market profit. But you still get some companies that will decide that, no, let me sell mine for 299, right? Or 295. Okay. Obviously, these people would default, or they would sort of, there is a defect. Okay. They would fail to cooperate. with the initial agreement. So once it happens like that, then the other companies will decide to punish them by also defecting on the kind of agreements that they've had. So basically, this is the whole idea. Please, I hope you guys understand.
Madam, I have a question.
Go ahead.
From
Mustafa, are you part of the you are asking the team, right? Are you part of
I'm asking you, madam.
which group?
I'm in group 7, madam. I'm asking a question based on the explanation you just gave us, the
Okay.
details you gave us. And from the details you were given, I'm thinking that doesn't mean that the there will be a movement between the two diagonals in the long term, either from cooperation to mutual defect or from mutual defect to cooperation.
Yeah, so depending on where they had initially decided to agree on, right? So assuming we had agreed to do this, and one person defaults, then obviously one person defects. There is a defect from the other person. The other person decides that let me move away for my own benefit. It means that person has played selfish, right?
Yeah,
So obviously you would move away from where you would have that initial,
cooperation.
cooperation,
Mm.
right, to a
Yeah.
defect.
Okay. Thank you.
So forever, there is going to be a punishment. It's like the other party is punishing the company that defected in the first place.
Okay. Thank you.
All right. So, and I think there is something that I mentioned in the previous group 7. You recall that I was telling you that the payoffs can be represented by functions and all that. And I think you saw that in this particular one, right? So you saw how they presented their payoffs.
Yeah. Yeah.
Yes, so like this, so that at the end of the day, if there is an increase somewhere, you're able to say that. So if this is greater than this, like we did in class the other time, right? So if this is greater than that, then it means that this is what they will play. If this is greater than this, it means that. So if the payoff for corporation is greater than the payoff for defect, then it means that there is a likelihood that they are going to, corporate if the payoff for this is greater. So you could have also put the same kind of idea in your analysis, where assuming they do the elimination and the payoff for that is greater than the payoff for the other side, assuming these people play this, then it means that the equilibrium will be that. So that is the whole idea I was trying to, bring out from your presentation. But it was a very good example that you guys gave. Thank you.
Thank you,
All right.
madam.
So I think we have two more groups. We still have some time. So we can pick these two groups so that we can end it next week. Then we'll take the question. We'll solve some questions together. Before those questions, I'll put the questions on the questions will come from the presentations that you've given, right? So more or less like examinable questions or assessments, right? So I'll put them on the LMS and then we will solve it together in the first few hours, maybe first 2 hours of next week's presentation, then we take the subsequent topic. So the next group can please go ahead. Please, I hope you are scoring and I hope you do understand what you are presenting. I do hope you understand what you are presenting.
Hello, Doc.
Yes, sir.
Yes, please. I going through the forms, I realized that one has to also rate him or herself or his
Of
or her
course,
group.
yes, you have to.
So, okay.
Okay. Please go ahead.
Hello.
Yes, sir.
Yeah, this is James presenting for Group 4.
Okay.
And our presentation is delving into Bayesian-Nash equilibrium, incomplete information, and Akerlof's market for lemons. So the overview of our presentation, we are going to analyze the strategic behavior under imperfect information. So under imperfect information, there are two major theories modeled around imperfect information and how it influences strategic behavior or optimal decision players in a transaction make. And one of the theory is the Bayesian-Nash equilibrium and the Akerlof market for lemons. So we will also delve into the application in markets, firms, finance, and policy. So if we say incomplete information economics, we have many scenarios such as firms may not know competitors' cost. Many economic interactions involve uncertainty about other agents. Investors may not know the true quality of firms. Investors may not know the quality of firms, although they want to buy shares or buy stocks, but they do buy. Buyers may not know the quality of products in the market, yet they have to make a decision to buy. And these situations are modeled as games with incomplete information. So one of the theory that we delve into was Bayesian game theory. It was developed by John Hassan in 1967. So this theory extrapolated from the classical Nash equilibrium and made an extension to it by analyzing how imperfect information influences strategic or optimal responses of players in a transaction. So he introduced what we call player types. And the player types refers to the private information that each player has that is not available to other players in the transaction. So it can be the cost of production, it can be credit risk, it can be health issues that each player has that the other players in the transaction has no idea of. Players form probabilistic beliefs about other players. So when a player wants to make a decision or a strategy, their strategy is contingent on the probabilistic belief ascribed to other players without actually knowing the actual type those players have. And decisions are made based on expected payoffs. So what is Bayesian-Nash equilibrium? In the Bayesian-Nash equilibrium, each player chooses a strategy that maximizes expected payoff. The strategies depends on beliefs about other players' type, that is the private information that other players have, which is not known to individual players in a transaction, and no player can increase payoff by deviating unilaterally. Therefore, strategies are optimal responses based on probabilistic belief. So a Bayesian game can be defined by the set of players that is the 1 to the nth number of players in a transaction, the types that is the private information available to each player in those transactions, and the probabilistic belief ascribed to other players by a player in the transaction before an optimal response can be made, and then a plethora of actions in the strategic profile, that is a mapping from types to actions, and the payoff function, the expected utility that a player is expected from the set of actions or strategies available to him. Hence, the Bayesian-Nash equilibrium is a strategy profile such that for every player I and every type T, so a player chooses the strategy that maximizes their expected payoff, given what they know about themselves, that is their own type, and the probabilistic belief they have ascribed to other players in the market. So we are going to take an example. So a market entry game. So we consider a market entry game between an incumbent firm and a potential entrant. The entrant is uncertain about the cost structure of the incumbent. So the players in this game is an entrant and an incumbent firm. And the belief that the entrant had made about the incumbent firm is that the incumbent firm might be strong firm, that is low marginal cost, or the incumbent firm might be a weak firm, that is high cost. So the entrants must decide whether or not to enter the market based on this probabilistic belief that the entrant has already made on the incumbent firm. So we're going to look at the payoff matrix. So the probabilistic belief that the entrant has made about the incumbent firm is probability that the incumbent firm is strong is 0.6, and the probability that the incumbent firm is weak is 0.4. So the strategies available to the entrant is to enter the market or stay out of the market. And the incumbent strategy also available to the incumbent firm is to fight the entry or accommodate the entry. So if we look at the payoff matrix, we could see that if the entrant enters and the incumbent fight, the entrant is going to get a negative payoff of 5, and the incumbent is going to get a payoff of 3. But we do remember that the entrance has already made a probabilistic belief that the incumbent firm might be stronger, because if you look at the probability, PS is greater than PW. And if you also look, if the incumbent firm accommodates the entrant in the market, the entrant firm will come and get a payoff of 4, while the incumbent firm, even though it is strong, it will get a payoff of 1. But if the entrant stay out of the market, the entrant gets nothing, and the incumbent, even though it is weak, it will maintain its payoffs. So let's see how we can derive the Bayesian Nash equilibrium using the strategy profile or the probabilistic function. So our expected payoff for the entrant, given the probability it has ascribed to the incumbent firm, that is 0.6 and 0.4, our expected payoff for entrants entering the market, if the entrant enters and expect the incumbent firm to fight only when strong, then the expected utility for entering the market is the probability of the firm being strong, that is 0.6 times the payoff, which is the -5, if the incumbent firm fights, plus the probability that the incumbent firm is weak times the payoff if the incumbent firm accommodates the entrant into the market. And at the end of the day, the expected utility or payoff that the incumbent firm will get is -1.4. So since it is a negative payoff, it is prudent that the entrant firm stay out of the market. And this Bayesian Nash theory is applicable in the real world. One is venture capital investment decisions. Investors normally face incomplete information about the true quality of startups and then the true quality of firms that they want to invest in. They just form a belief about maybe the CEO is good or the CEO is visible on social media. So the entrepreneurial ability, technological viability, market potential. So the investors will just form a belief and then make a decision to invest or not. Same applies to government procurement bidding. So the government will announce a contract, and the bidder, since it is competitive bidding, each bidder do not really know the valuated cost other bidders are trying to bid. And then the surpluses the other bidders will add to the costs valuated by the other firms. Yet everybody wants to be selected, while the government will choose the bid with the lowest cost. So at the end of the day, the surplus plus the cost of the project will converge to the true cost, and the government will make efficient contract allocation. Same also applies to strategic competition between firms, because firms really, in a real world situation, do not have access to private information of the other firms. Therefore, they just form a belief. And upon those beliefs, they also make the optimal choice in their strategy profile, as well as trade negotiations between countries, where countries, either international trade or implementation of quotas and tariffs, do not actually know what the other or the affected country productive capability is. Yet they make decisions due to uncertainty in the market. So we move on to the Akerlof theory. So this theory is based on information asymmetry. So it occurs when one party has more information than the another in the transaction process. So common example is the used car market, the insurance market, the labor market, and the financial market. So we are going to delve into the Akerlof market for lemons. So this was developed by the economist George Akerlof in 1970, and it demonstrates how quality uncertainty can cause market failure. That is, low quality products will drive out high quality goods in the market for lemons. So we use a real world example, such as the used car market. So in the used car market, we have two types of cars. That is, we have a quality car and a bad car, or a lemon. And then the value that is ascribed to buyers and sellers. For example, a quality car is valuated at $10,000 by buyers and is valuated at $8,000 by sellers. A bad car, or a lemon, is valuated at $4,000 for buyers and valuated at $3,000 for sellers. And the hint is that buyers cannot distinguish between quality. So if you're going to buy a used car, it's highly difficult to know if it is reliable and it can take you wherever you want to take it. So how does buyers make an optimal decision under this information asymmetry? So if the market, assuming a market houses 50% good cars and 50% bad cars, and sellers know which type of car they have, but buyers don't have that luxury, then we can write that proportion of good cars in the market is P, and the proportion of bad car in the market is 1 minus P. So buyers' expected value for a randomly selected car is, so if a buyer is going to buy the car in the market, since there's 50 chance that either he's going to get a good car or a bad car. So what is the optimal value the buyer will ascribe to a car, since it does not really know if he's going to get a good car or he or she is going to get a bad car. So we can write it as a probability of buying a good car at a premium, which is the value to the buyer, plus 1 minus the probability of buying a lemon, which is the valuation to the buyer, where P is the market scenario, because we said it houses 50% good cars and 50% lemons. So we are going to get 0.5 times 10,000 plus 1 minus 0.5 times 4,000, which is going to give us 7,000. So the expected value a buyer ascribed to getting a car in the used market is $7,000, even though the buyer has no luxury of knowing whether or not the car is good or bad. So the expected value is $7,000. But sellers of good cars will not sell at this price because their reservation price is $8,000. So we saw that quality car, the last price, as we say it in Ghana, is $8,000. Yet buyers are coming in with an optimal value of $7,000. So if you are a dealer and you are selling good cars, your only option is to withdraw from the market because you can't sell your good car for 7,000. And this is an opportunity for people who are selling bad cars or lemons. So this generates adverse selection where low quality cars dominates the market. And why does it arise? Adverse selection arises because good cars exist the market, as we said earlier. Dealers who are selling good cars will exist the market because they can't sell their good cars for $7,000 valuated by the buyers before coming to the market. But those who are selling bad cars will be happy because they can sell the lemons, which is 4,000 for $7,000. Buyers anticipate low quality. And since buyers are pessimistic in the market, they anticipate to buy a low quality car. And price will fall further because they will continue to negotiate downwards and it will cause a death spiral.
Is it my network or James is off?
And the market may collapse.
So his line just went off. Yeah.
Is Evans around?
Okay,
Evans.
thank you.
James
Okay.
line, let me quickly share my screen.
Ivan, are you the one showing the slide for it?
It's James. I'm trying to share.
Sorry, no, my network just got disrupted.
That's
So
right.
I'm
Okay.
reaching.
Go ahead.
Please, can you see the slide?
Yes, I think you are on the last few slides.
Yeah, sure. Please, Evans, can you do justice to this slide for us?
Okay,
Can you
so
please do that in the next 2 minutes? We are running late, please.
okay, so I'll just summarize that. So with that, in the real world, there's examples on the health insurance market. Because the insurance company don't have complete information about the insurers that they are insuring, and the insurers also don't have a complete information. There is adverse selection and moral hazard as well over there. Same to the credit market, financial security market, and the labor market as well, where employers don't have complete information about their potential employees, where employees also rely on their certificate and maybe interview. Employers form decisions based on those signals and then make decision on the pay and other things. So this sum up to the information asymmetry in the market, word market. Yeah. Thank you.
Okay, so are you guys done?
Yes, please.
Okay, so Evans, I thought the theory as far as who presented, as far as James was talking about, was a case where the sellers have a complete information that the buyers do not have a complete information. And because of that, the buyers would propose sums that are lower than what is supposed to be. Based on that, the sellers with the quality product will exit and will be left with the lemons.
Yes, please. That was on the Aklov theory of lemon market, lemon forecast.
Okay.
So because
I'm saying that because of the examples you gave for is it the insurance and the
yes, please.
employment? That's why.
Yes, please.
So the key point here that we need to note is asymmetry of information and also adverse selection, isn't it?
Yes. And
Okay.
moral hazard.
Okay. All right. So thank you so much. Guys, any question? Nobody has asked a question so far. I think it was only Mustafa who asked me a question. Nobody is asking anybody because you don't. But now you four finished presenting. It's left with the large group, so you can ask questions. Nobody will ask you a question.
Is this group 4?
This
Yes.
group 4, yes.
There is group 4.
He's only asking to score.
No.
Yes, madam, you are right.
Yeah. You're not asking any question. Okay, guys, go ahead. Group 5. Group 5, please let's be snappy. Let's do this in the next 10 minutes. We need to leave here soon. Group 5.
Hello, Doc.
Yes, sir.
This is Peter from Takrady, Group 5. We are from Takrady.
Hey, Aze. Orokodo.
Record,
Okay.
madam. So, Bismarck, please, if you are around, share your screen. Let's start.
Atu,
Yeah, where's Mark?
yeah, please help me with the screen sharing.
Okay, that's okay. Please give me a minute.
All right. Good.
Is I'm sharing.
Off one of your mics. Okay, so I can see the screen now. So, good evening, Doc and colleagues.
Yes, good evening. Go ahead.
So, we are presenting on repeated games and then finite repeated games using the rare scenario. So, beginning, we're gonna look at what repeated games are, and they occurs when the strategic interaction called a state game is played multiple times by the same players instead of interacting once. Sometimes the players meet repeatedly over time and make decisions in each period. In a standard one shot, players only have one focus, immediate playoff. However, when games are repeated, players must consider future consequences of their current actions. So, looking at the components of the repeated games, we have the players, the strategy, and then the payoffs. So, one, we look at the strategic thinking, where players now have to plan and move accordingly, and then the maximum payoff of which they'll get from their strategy, and then the real life application, where we also have to know how this can help us in politics, business, economics, and then revolutionary biology. Next slide, please. Okay, so as I explained earlier, the players will now have, they could be the firms, the individual,
So,
the
Bismarck,
organization.
please skip this slide. Kindly
Okay,
skip this slide because this one is the basic part so that you move
okay.
on to the main issues. Thank you.
So when we talk of repeated games, we say that we have some players and then we have to make some identical decisions. And then these decisions must also interact repeatedly. And then sometimes we say that the past actions influence future strategies or beliefs. So history matters. And then strategic evolution, players can condition their behavior on previous outcomes. So this explains why competitors might cooperate despite having conflicting interests, how reputation develops, and why business strategies can sustain cooperation. So we basically have two types of repeated games. We have the finite repeated games and then infinite repeated games. When we talk of the finite repeated games, we say that players have fixed and known number of times. They also know exactly when the game will end. This knowledge enable backwards introduction reasoning. So let's say maybe they have number of times rounds 3 times or 4 times, and also they know the end point, and then the backward induction also applies over there. And when we come to the infinite repeated games, players also do not have the fixed end point. So they do not know whether this is our last chance or we will still have another chance to also play the game again. And then it also have a discounting future payoffs and cooperation more sustainable because they don't know whether this is their last chance or they'll still have their chance. So more time they used to have this option and then cooperate more on this aspect. So sometimes we say that, first of all, when we talk of the finite repeated games and the end game problem, we say because the games is fixed and we have the number of rounds that they have to go, they precisely have to have the fundamental shapes of their strategic thinking throughout the entire game. So one, we have the final round. Let me take it from the first round. The detection from the beginning when they start the game. So for instance, when a game is being presented to them, they have the chance to either defect or cooperate. So at the possible beginning, they might decide not to cooperate because they don't have the options. So they don't know what the other one will choose or what the other one will choose. So in the beginning, they have the probability of not cooperating. And then the second round comes in, then they have the chain of reaction continues backward. And then they have the also final detection round to also know the players what they detected earlier and others. So when they get to know these things, now the final round they have no future punishment possible. Both of them can also detect from that particular game. So the critical insight is in the final round. There's no possibility of future punishment for detection. This creates an incentive to detect in the last round with the triggers detection in the earlier round throughout backwards induction. And with this game, most of the time during the repeated game, the Nash equilibriums are defects. Most of the time during the repeated game, the Nash equilibriums are to defect to that. Next slide, please. So we're gonna take this classical example to look at the. So looking at this, we have the prisoner's dilemma over there on the repeated game process. So this is one of the most common games in the theory, illustrating the tension between individuals and collective rationality in a single state game. Defection, and then also cooperation, dominate and cooperation leading to, so as I said earlier, this one defection. So let's look at player A and player B. Now, when player A cooperates and then player B also cooperates, both of them have the chances of serving 3 years imprisonment. And when player A cooperates and player B also defects, player A have the chance of 7-0, which means they'll be free, and then player B have the chances of also going to prison for 5 years. But on the other hand, when player A defects and then player B also cooperates, then it means that player B is rather going for 5 years for player B to be in 4-0, which means player B will be free. So it's more like Chama to me's case. Later on, we got to know that the manager came out to say that he is not part. He will be the witness for the state prosecutioner. So it means that such scenario was applied over there. So since this one, they have repeated option of maybe asking them such question again. They will go on to ask them. So since they do not know, they can either go by the tick for tat principle or grim trigger. So if they are going for the grim trigger, then it means that both of them will now have the mutual cooperation. That one, we are all going to defect. For that one, all of them have decided that we are going to defect. But on the other hand, if they are going for the tit for tat, no, if you say that we are defecting, and when you come back to realize that one of your partner did not defect but rather cooperated, then you also in the next round will decide to do what? Cooperate in order for him to get the punishment so that you will be free. So when it happens that way, it will pain him, and then the next time you can get the other partner also defecting from that particular game. So we say that it creates mutual detection and then temptation, because detection against the corporation is highest individual payoff from this particular example given. So it means that one, if both of them cooperate, they are going to get 3 years, 3 years. When both of them detect, they are going to get 1 year, 1 year. So it will be dominant for them. The dominant strategy for both players will be the 1-1, and then the superior for them will be the 3-3. So they will choose the 1-1 over the 3-3 when it comes to this classical example I've given. Next slide, please. So using the backward induction and state perfect equilibrium, this is a powerful reasoning method for analyzing finite repeated games. Players start by analyzing the last round, then work backwards to determine optimal strategy in the earlier round. So this one, because the history helps them in deciding whatever they should do, they analyze it using the last one to get to know how they are going to start on this ones. So final round one, in the round one, no future punishment exists. Players choose Nash equilibrium at the game state. Defection in the prisoner's dilemma. And reason two also to the previous one, we say that knowing players will defect in the first one, cooperation cannot be sustained in the other round. So players defect earlier. And then continue to the backbend. We also that this logic cascade background through all rounds. They change reaction to the defection in every single round. And then the SPE outcome, the sub game perfect equilibrium requires detection in all round. Cooperation cannot be sustained, even though it will yield them higher total payoff. Once they decide to cooperate, it will yield them higher payoff, but they will decide not to. So we say that if both cooperate, moderate benefit for them, which will be the other one. But when they start to defect, both of them will low payoff, which will be the 1-1, unlike the one game short. Please, next take. So using the telecom competition, for instance, competition, for instance, firms engage in repeated strategic interaction through pricing decision, promotion, and service offering. This ongoing competition closely resembles a repeated game with important implications for market dynamics. So firm A and firm B, when there's higher price, both of them will get 8-8. When there's low and high price, 2-10. When there is a low and high price for the firm A and B, it will be 8-10 and 2. But when it is low for A and low for B, there's going to get 4-4. So it means a high price equilibrium. If prices maintain high, if both of them maintain high prices, they enjoy stable profit of 8 each. And this resembles cooperation. When they cut the price of initiative, if one also lower its price, it gain market share of increased profit to 10, while the other one drops to 10. And if both of them also lower, the price war will ensure that they also reduce the profit for each to 4. So with this, that they know the finite they use. So because they have the finite, they can also have the backward invention to predict whether the firm will engage in the price war in all the periods, which were not able for them to sustain the cooperation of the high price outcome. Please, the next slide. So these are the takeaways of the. Now, repeated games also provide crucial insights in how strategic behavior changes when interaction continue over time, and distinguish between finite or not infinite horizons has a profound implication for cooperation. So let's look at the time horizon matters. Finite games with known endpoints leads to backwards induction and differentiation. Infinite games allow sustained cooperation through punishment strategies. And then cooperation merges repeatedly, interacting enabling cooperation that would be impossible in one-shot games. Reputation and future consequences create incentives and then for restoration. And looking at real life application, we say that price competition, trade negotiations, labor contracts, environmental agreements, and repeated business relationships all fit the repeated game framework. So to conclude, I basically get to conclude that repeated interaction fundamentally transforms strategic incentives. So we say that it evolves over time, showing that future expectations can strongly influence present decisions in competitive environments. And it also analyzes the final repeated games, highlights the importance of backward induction and equilibrium reasoning, which are central to in the game theory. And therefore, understanding repeated games allow the economists to better explain real life or real world behavior, such as firm competition, as I mentioned earlier, negotiation, as I mentioned, and then long-term cooperation in the market. So on this note, I'll thank you for your attention, and I will be glad for any other questions. Thank you very much.
All right. Thank you so much, Bismarck and the rest. Okay, so I think you've brought another twist to what we were learning initially, right? Because I think in the initial stages we had learned about the repeated games. Now, sorry, about the infinite repeated games. And the twist with the finite games is that at the end of the day, we are able to use the backward induction to solve this whole, um, um, game. So we are able to find equilibrium even using the backward induction because we have an idea of the outcomes, the possible outcomes at the end of the game. So basically, what I see with all the presentations that we had done is that you guys have been able to work around some of the concept, in fact, most of the concept, but my question here is, do you really, really understand what you have presented on? I mean, some of you came out in a way that assume that you do understand it. Others, I'm not too sure. And so I'll be on standby within the week. If you have any question whatsoever, please let me know and I'll be happy to engage. Also, my next point is that we are preparing ourselves for, uh, we are already out there, right? Most of us are working, but day in, day out, as we try to upgrade, as we try to get more from our education, we are preparing ourselves for, bigger task, right? And so I do hope that we try as much as possible to um, look at our presentations again. Okay. I really like the way most of you had presented. Asking any questions, that is why. But
Oh,
if you have a question, please go
oh,
ahead.
but right away because you came in, so I thought maybe you finish it.
Oh, sorry.
I
Because
had a
the
I
initial ones, nobody asked anything, which is why.
yeah.
I'm sorry.
So
Go ahead.
oh no problem, madam. Yeah, so I wanted to ask you, some of these games, right, they have their pros and cons. And if
Right.
any participants have the option to pick and choose which game to participate in, they would have gone for the one that is most convenient. Particularly in this repeated game that we saw, we have one that uh, you can have endless options to continue playing, and it will expose the various options and the various strategies and openings we use, which clearly gives an advantage over some other games. I wanted to know if there are penalties or ways to mitigate maybe people engaging in a game that is more advantageous over the other. Basically, like this one, for instance, if you want to engage in an endless game compared to one that you have a finite um, participation, number of participation, are there mitigative or penalties that will be sanctioned on you before you can partake in such games? That's what I wanted to know.
Okay, thank you so much. So we had explored several games. The whole point is that at the end of the day, we are faced with various situations in life, in businesses that requires certain skills, and the setting might be similar to any of these games. I hope you understand. So, for example, assuming you are in a monopolistic market and all of a sudden someone is trying to replicate what you are doing, right? So I mean, on top of my, let me just use this as an example. It is not accurate, right? But assuming when we pick Zoom Lion, right? It's a monopolistic firm. I mean, it is not true because we still have some other, sanitation way, but I'm just using that as an example. And there is another giant company trying to enter the market in Ghana. Now, at the end of the day, Zoom Lion will be faced with this situation. So this is a market. The market is faced with that situation. Unless the other company is saying, I'm coming in the market and in the next 5 years I'll exit, then that's fine. I mean, that is defined. But if you know that these people are coming into play and definitely you are going to be, competing forever, then you obviously know that you've been faced with a situation where the game you are going to play will be an infinite game. I hope you understand what I'm trying to say. So sometimes you don't choose and pick the game, right? Because it's a situation that you find yourself in. But there are cases where you can also choose and pick a game if you are the one designing the strategy, or if you are the one looking at, you are the one designing the game. Okay. So for example, there is a contract. Maybe you write a proposal to an organization for funds, and you intend to engage another company, or you intend to look at possible, collaborations or whatever. You have set the timelines to a particular time. Or, I mean, all these things are because for every business decision, there is some sort of strategy. And depending on the kind of situation that you are in, then we can say that this particular situation is similar to that of let's say a prisoner's dilemma, but it's a one stage game, a single stage game. Okay, or this is similar to this particular game, Battle of the Sexes, but it's a single stage game, or it is an infinite game, or it's a finite game, depending on the period. Sometimes you can choose and pick if you are designing it, but in cases where you're not the one designing it, you will still find yourself in the game and you have to play it. I hope you understand what I mean.
Yes, sir. Yes. Thank you so much.
Yes, so basically what we are learning as far as the game theory is concerned is just to help us to make certain business decisions that would help us get payoff that is optimal. Okay. At the end of the day, the decision that you took, you realize that, no, this is the best decision I've taken, irrespective of whatever happened, or this is the best decision. I couldn't have done anything better than this decision. So you learn all the aspects, like all the types of games, because you would be faced with different situations at every point in time.
Thank you. Thank you so
Matthew, I
much,
don't
Doc.
know if I've answered your question.
Yes, yes, Doc. Yes, Doc. Well
All right.
explained. Thank you.
Right. So, please, any other?
Doctor, please, concerning the
Yes, Priscilla,
scores
go
on
ahead.
the Google form, yes, please.
Yes.
Said we should grade it over 10. I want to find out, is it whole numbers or can do fractions? Or
Please, any goes. Even if you want to give 1/2, I don't mind.
okay.
Even if you want to give, I mean, any number that you pick, at least I know that 2.999945 is less than 3. So the only thing is that it has to be a number between 0 and 10, and not a negative. Or Priscilla, you intend giving somebody -1? Like, who owes me? I think somebody even owes me. Somebody owed me in class the other time. Who was that? Who?
Majid.
Majid. So if Majid owes you, I want to give him -2, then that would be a problem, because I'm only taking from 0 to 10. All right, thank you so much. All right, guys, if we don't have any question, I would like to say thank you very much for your time, and thank you very much for spending time to, work on these presentations out and treat you all to take time again to really understand the concepts that you have presented. I do hope you understand them, but if you don't, and maybe there are things that you are struggling with, within the week, we can talk about it. When we meet next week, we'll solve questions, okay? We'll solve should I call them examinable questions, or just to have an idea of what could be asked, just to have an idea of how things might look like as far as game theory is concerned. And if we are able to use, like, let's say the first 2 hours to do that, the subsequent time we will use it for the other topics. I think we would need 2 meetings for the next topics. If you are able to grasp everything on time, then we'll use the last maybe the last 2 hours of the semester, technically for the teaching, also to look at questions as far as those topics are concerned. Please, if we don't have any question, I would like
But,
to. Yes, sir.
Madam, please, will we be able to get the questions within the week before we meet?
Yes, so I'll send some on the LMS.
Okay, please.
Or through the class reps. I'm not saying those ones are going to come in the exams, oh. Nene. All I'm saying is that,
just examinable questions.
Well, yes, but they are just to help you understand the concepts better. You get it? And how best you would apply it. I hope you understand my point.
Yes.
Yes. I'm not saying you are going to see those ones in your exams. No, not at all.
Yes.
Okay. So any other? Peter, did you have a question?
So
no, Doc.
Okay. Yes, Mustafa, go ahead.
So within the week, as you offered to support if the need arises,
Yes.
how do we get in touch?
Oh, you can talk to Evans. Evans will let me know. If it is something you want to discuss with me, you will have to call me.
Okay, then Evans, okay. Thank you.
All right.
Thank you.
So if it is something that it's something that could be done through a message, you can do that. Other than that, if you really need to talk to me, you just call.
Okay, thank you.
But please don't call me after 9. As for us, we are matured, so I know we won't do that. As for the undergrads, there are times I get calls as late as 11, and I'm like, oh my goodness. So I'm sure as for us, because we are, matured, I wouldn't get that from you. So do call me when you have.
Okay.
If you call and I don't pick up, you can send a message. Just drop a message that you wanted to discuss something on this with me, and so which was why you called, and I'll call you back when I'm less busy. If I don't pick up, maybe it's because I'm busy. So I'll definitely return the call. But if you add a message, that would help. That would prompt me. So
Okay, thank you very much.
thank you too. Okay, so if we don't have any question, Grace, are you there?
Yes, I'm here.
Okay, forgive me. I called you because you were the first person to present. And once you are the first person to present, in most cases, the first people run away right after presentation. So I'm glad you are still here. Thank you so much, and do have a good evening. Grace, do you have any question for me?
Thank you very
Yes,
much.
but I'll see you back though.
Back door, I hear. All right. Thank you so much.
Thank
All
you.
right, guys, please enjoy the rest of the weekend. Bye.
Thank you so much.